So this brings us to the crossroads when we talk of uniprocessor performance. So here is a chart that is kind of captures the performance that we have been seeing and what we expect in the future. So this on the x-axis you can see it runs all the way from 1978 up to 2006. On the y-axis we see the performance versus a wax machine. This is one of the older machines we looked at as the basis for our results. So if you see the initial trend, and this is where we look at from say 1978 to 86, this is before 8086, the revolution that started, we see that the performance improvements was around 25% per year, right? This was in 70s and early 80s. So we sit around 25% per year. Most of it was because of improvement in transistor density. Most of it was because of some microprogrammed control and so on. When it goes beyond 1986 to say around 2002 or 2004, we started seeing 52% per year. Now that was the golden period of computer architecture where we were able to increase the clock rates. We saw the transistor scaling. We took a lot of performance gains through instruction level parallelism, where we started looking at different instructions and we said how can we execute these instructions at the same time and so on, and the growth rate was fantastic, right? We came to 2000 to 2004. This is where we see an inflection point. This is where the clocking could give us some problems, right? So some of the things we spoke about, if you look at the power density started playing a major role. So at this point is when we started seeing a paradigm shift. We started seeing going into the design of multi-core. This is what the industry adopted. Instead of having a uniprocessor or a single core, why don't we do multi-cores? Why don't we have more than one cores? Having more than one cores allows us to increase the performance without having to go for higher clock rate. So instead of having one processor running at 4 gigahertz clock, why don't we make two processors each at 2 gigahertz clock and try to see if we can improve performance? Now, because we have multiple cores, we have increase in transistor density, which increases the power consumption, but we also have the opportunity to tune off some of them, right? We have other opportunities where we could look at programming models for these processors and so on. However, the growth rate is now not anymore 52% per year. We probably will see 20 or 25% on a yearly basis because of other issues that come in keeping all the cores busy and making sure that we can get the desired performance from these cores and so on. So here is, the crossroads, and this is where conventional wisdom and how it compares to computer architecture. So the old wisdom was power is free, right? Transistors are expensive, right? This was very true. Transistors was expensive, but nobody worried about power. It was not even a criteria when people were designing 8086 or 8088 and so on. The new conventional wisdom is different, right? Power wall is what we are going to hit because power is extremely expensive, although transistors are free now. Right, because we are able to scale transistors into much lower numbers, right? We can go up to 7 or 9 nanometers. There's technology trends to do that. Whereas the power is going to be very expensive. And in fact, today we spend a lot of effort in reducing the power density because power is a first order constraint. So first, people design what is the power budget for the system and then see what is the performance that we can get, because power is becoming very, very important. Both dynamic power, which is the power that is consumed when transistors switch, and the static power, which is because of the leakage, right? So when you have when you switch the transistor off, also there is some current that is flowing through these transistors where static power is consumed, which is also becoming a big criteria. Given that there are billions of transistors, right, active in on the chip, it can clearly cause a lot of power surge. Reliability becomes an issue, right? Because things can heat up, things can fail, and with all these billions of transistors, it's not very simple to keep switching them on and off. So power wall is a major constraint today. The old conventional wisdom is, yeah, there is sufficiently instruction level parallelism. That is, we take instructions that are independent, executed. We can exploit this via compilers, or we could do out of order execution, right? So we don't have to go in order with all the instructions. We pick instructions out of order, put them into the processor, execute them, see performance gains. We could speculate, which we do, VLIW, and so on. So we should have sufficient improvement in performance. The new conventional wisdom, we are hitting the IPL wall. That is ILP wall. That is the law of diminishing returns when more hardware is put into it. Why is that? Because today programs have a limited number of instruction level parallelism that can be exploited. Some programs have absolutely none. That is, all instructions are dependent on each other, which makes it more and more difficult to exploit it. Now, this is very true, right? If you write a loop of a code with a loop and you say for something and you have 2-3 instructions, there's a very strong likelihood that those 2-3 instructions will depend on each other. And the more dependency is there, we cannot exploit this parallelism. This instructional parallelism cannot be exploited, and we need to look at other, such as data level parallelism or thread level parallelism, and so on. The old wisdom was multiplies are slow, memory access is really fast. That is, multiplies is a bunch of addition and shifting, and memory access, that is to access any memory, is very fast. The new wisdom, we're hitting a memory wall. Why? Because memory is off chip, right? DRAM. Going off chip today has become extremely painful, and multipliers are extremely fast. That is, anything on the chip, any logic that you want to implement because of the explosion in transistors, you can have function units that can do that work for you. Right? For example, if you want to speed up multiply, you parallelize it. You write algorithms where you have different transistors, right? You can have different modules which do partial solution before you get the complete solution. So you can speed up multiply. Whereas memory, well, memory is off chip, and if it is off chip and as transistors are scaling, it is going to take a long time to get to the pins on chip and then go off chip. Today, the difference between an on-chip access and an off-chip access can be anywhere between 10 to 15 cycles for an on-chip access to 100 to 200 clock cycles for an off-chip access. So you do not want to go off-chip, right? You do not want to go off-chip to access all the data because it's going to be very expensive. And for 200 clock cycles, you have the processor sitting idle, right? So multiplies are fast, DRAM accesses become really, really slow. And this is where we have the memory wall, right? So the old convention wisdom is uniprocessor performance is doubling. This is what we saw, 52% growth rate and things going very well. So doubling almost every 1.5 years. The new convention wisdom is you add all these three walls, the power wall, the ILP wall that is not getting enough improvement in performance, and the memory wall, because you see memory slowing down, multiplies becoming fast. We get into what we call as a brick wall, right? We really are in trouble here. And the uniprocessor performance now, it won't double every 1.5 years or so. It will probably take 4 or 5 years to double, and that is your growth rates are going to go slower because we have to consider the power density of the chip. Then we need to exploit parallelism to improve performance. We need to have new programming models because we have all these multi-cores that have to synchronize and solve the problem. So there's more communication. There are other constraints that will reduce the performance. So the sea change in chip design is what we have multi-cores today, right? Everything is multi-cores today. We can see the doubling of processors per chip. So we had 2 cores, then we have 4, today we have 8, tomorrow we'll have 16, 32, and so on. So it's almost like the number of cores are going to double. It's not exactly true that we are going to get double in performance, right? It's probably going to be less than that, maybe 20%, 25% improvement in performance. And we're going to see more simpler processors that are going to be more power efficient. And this is a very important criteria. That is, all our designs, all our processor designs, they're going to be more power efficient, and from there we are going to see how much performance we can extract from them.